All right. Now on to our final speaker of the day is Tom DeJong, who is a final year PhD student with Martin Escardo at the University of Birmingham. And he'll be speaking about order theory and propositional resizing in HoTT.
Okay. Thank you, Carlo, for the nice introduction. And thanks to the organizers for letting me speak here. So I'm going to skip right through. So just to say a little bit on the introductionary side. So in my PhD, I'm developing domain theory in constructive and predicative HoTT or Homotopy type theory, Univalent Foundations. I'll use the two interchangeably. And predicative here just means without propositional resizing. I'm going to say more about that in a second, make that more precise, just in case some of you are not completely familiar with that. And so sort of what I set out to do was to see, was to look at HoTT as a sophisticated foundation for mathematics that is sort of constructive by default. And then we wanted to see, can we do domain theory within this system and what does it look like? And is it nice and formalize a lot of it? And so domain theory is a branch of order theory with applications in semantic programming languages and topology and algebra and higher type computability. So it's a very nice sort of subject in theoretical computer science. And we wanted to see how HoTT would tackle it. So in this talk, there's a few sort of motivating observations, which then leads me to the main point. So in some other work, I constructed the Scott model of the programming language PCF in HoTT. And the things you use to interpret the PCF types, DCPOs, the directed complete posets, they're typically large. So to give an example, what happens is you have the Martin-Luft type of natural numbers in your lowest universe, U0. But then when you interpret the PCF type of natural numbers as a DCPO, then this lives in the next universe, U1. So you have this jump of universe levels. And you have a similar thing happening in point-free topology, where the locales of the frames are typically larger, they go up one level. And the main point of this talk is to show that this largeness is unavoidable in HoTT unless we assume propositional resizing. That's sort of the main point of this talk, and I will spend the majority of the talk just trying to make this into a precise statement and then something you can prove and make sense of. This is based on our 2021 FSCD paper, which was joint work with Martin Escardo. Okay, so here is sort of the informal formulation, if you like. So the theorem is going to be that various kinds of non-trivial posets are small in HoTT if and only if propositional resizing holds. So we're going to have an if and only if statement here. But the most interesting direction is that this resizing is really strictly necessary. And I would like to offer the following result by Peter Freyt in category theory. So this is in an impredicative setting, but it sort of primes you for what I'm about to do next. And the result is saying that a category with small co-limits is small if and only if it is a poset. So one way of looking at Freyt's result is saying that in category theory, you have to take size seriously. If you want to have small co-limits, then your category better be large. Otherwise, it's not going to be a category at all. It's just going to be sort of a degenerate category. It's going to be a poset. And so one way of looking at this theorem, at least the informal formulation for now, is that if we don't have propositional resizing available, if we sort of working predicatively, then you already have to take the size seriously at the level of posets. So that's sort of what's going on here, and is a good way to think of this. And we're going to be using some notions from category theory as well to sort of implement this. Right, so I should say a little bit about what's to be made precise within this informal formulation. So obviously the first thing I'm going to do is I'm going to talk about propositional resizing, what exactly I mean by that. And then there's these various kinds of posets. What do I mean by when are they non-trivial and when are they small, and so on. And then the precise formulation will be a theorem of HoTT. And so it's rather than like some meta theorem about the system, it will be a theorem inside the system. And in particular, the way we set up propositional resizing. Okay, so let's jump right in. Let's look at the resizing. So we start off with some sort of universe U, a type universe, and then we simply collect all of the propositions in that universe, and we call that type omega U. So this is a little bit like the sub-object classifier in tuples theory, except now it's important to notice that this omega U, a priori at least, lives in the next universe U plus, because you've taken the sigma type over all P and U here. So it's going to jump one level. But then we make the definition that a type in U plus is small if we have a type in U that is equivalent to it. So this is like essential smallness in category theory. We don't actually stipulate that X itself lives in U, but at least we have some type in U that is equivalent to it. So sort of for all intended purposes, X will sort of live in U. And then this resizing axiom, omega U resizing, simply asserts that the type omega U is small. And there's an open question here, at least as far as I'm aware, that's open, which is, does omega U resizing have a computational interpretation like univalence was given in cubical type theory? Now, obviously, I'm not going to answer that question in this talk, but I thought it would still be interesting to have a look at that. So next up, I want to say a little bit more about axioms versus rules. So Voevodsky proposed propositional resizing rules. So one of them was that instead of having this type in U equivalent to omega U, you just postulate that omega U itself lives in U again. Or you could even say that it lives in the lowest universe, for instance, if you want a somewhat stronger resizing rule. But what we're doing in this talk and in the paper is we're looking at the resizing axioms. So we're going to have this thing up to equivalence, and it means you can prove theorems about it in the system rather than metatheorems, right? So you're not proving things about structural rules of a type theory. And also, the rule is not known to be consistent, but the axiom is, because the axiom follows from excluded middle, which itself is validated by the simplicial sets model. So that's another difference here. So that's where I'd like to go next, talk a little bit about excluded middle and the resizing. So excluded middle, if you have this in U, so if every proposition in U is decidable, then you have omega U resizing. And without showing all of the details, the reasoning is kind of simple. If you have excluded middle, then there's only two propositions, namely false and true. And so that's everything there is. Therefore, omega U must be equivalent to the 2-point type, which lives in the lowest universe. So you can have all the resizing that you want. But has the important consequence that if you seriously want to study this omega U resizing, then you have to work constructively, because otherwise you're just assuming, you're just proving things about true, which is not useful at all, of course. And the fact that we're working constructively is going to be important later on, because things are going to be a little bit subtle within our constructive framework. And finally, before I sort of close off this section, I would like to introduce this variant where I consider not stable propositions. So a proposition is not stable if it is implied by its double negation. So in particular, all negated propositions are not stable. And I can collect all of those in the universe and make this new type omega U not. And I can have a similar resizing axiom where instead of resizing all of omega U, I'm more modest and I only resize the not stable ones. And then there's weak excluded middle, which rather than deciding P, decides the negation of P. So it says either not P holds or a double negation of P holds. And weak excluded middle is equivalent to De Morgan's law, if that's more familiar to you. And then you have a similar result where weak excluded middle in U implies the resizing of omega U not. And so this is going to come back in a couple of slides. So we're going to have, in this talk, we're going to sort of study two versions of propositional resizing, omega U resizing, and the resizing of not stable propositions. So next up, I want to go to these various kinds of posets. But first, it's good to have a little bit of a primer. So we look at these small at complete posets. So for instance, a poset X will be called a U-sup-lattice if every family I to X with I in U has a supremum in X. So basically, this is like having small co-limits, right? You index by something small. In this case, we index by something in U, which we think of as small. But the carrier and the values of the partial order are not required to live in U. They can be in some other type universes. And then once you have this, it's straightforward to define what a UDCPO is, because you just restrict to directed families, right? So you just translate the notion from a directed subset to a directed family, and you ask for suprema. Whoops. So the main thing here is that you just restrict the index types. That's the main point. Okay, so then, of course, this would be no good if there were no examples, but there are plenty of examples, fortunately. So for instance, the power set, which we realize by looking at predicates on X into omega U. So this will be a U-sup-lattice. And if you're given I in U and some family of subsets indexed by I, then you just translate the set theoretic union into this predicate style, and you can know that this type, this exists here, does indeed live in U. So that's all good and well, but the power set itself lives in U plus. So here again, you see this pattern where you want U-sized suprema, then you have to live with the fact that the thing itself, the carrier, lives in the next universe. And similarly, you can look at omega U, which is a U-sup-lattice when you order it by implication, and with suprema given by existential quantification. Okay, and so next up, we're going to be introducing a technical notion, which is going to capture a very weak notion of completeness, sufficient to make the theorem go true, but also sort of interesting enough that it's still captured by a lot of examples. So it's a lot of like U-sup-lattices will be an instance, U-DCPOs will be an instance, and so on. So that's where, we're actually, before I do that, I should talk about U-DCPOs. So there's one more nice example I'd like to show, which is the lifting. So what you do is you take something in set in U, and now you consider the lifting, which is a type of propositions and a map from that proposition into X. And now the idea is that an element X in X gives you an element of the lifting just by taking the proposition to be 1, and then you take the map from 1 to X given by little x. But in general, P is the domain of definition of a partial element. So this is a sort of a subtle, like constructively good way of dealing with partiality using this lifting. And that's what you use in the Scott model. So in the Scott model, you interpret the PCF type natural numbers as the lifting of n, which then lives in the next universe again, because you're using this omega right here. And for the function types, you use Scott continuous functions. And again, you have this jump. So that's what happens. Okay, so now I'm going to talk about this weak completeness property. So this is delta U completeness. So the idea is that this is going to be a very weak sort of completeness that will allow us to prove the theorems that we like. So we're going to start off at a poset X, and we're going to say it's delta U complete if for every proposition P in U and elements X below Y, this family here has a supremum in X. So what does the family do? Well, the family just always includes X, because you just take the left component here to X, and it includes Y exactly when P holds. So it's a little bit like the subset X and then union Y if P holds. And the idea is that once you have this, which is a sort of generalized subsingleton completeness, this will sort of allow you to, by looking at the supremum, you will be able to say a little bit about the proposition P. That's the idea. So I'm going to say a little bit more. So with excluded middle, it would be good to sort of look at this classically. Everything is delta U complete, because what do? You take the proposition P and you just decide, is it true or not? If it's false, then this family just contains X, so therefore the supremum must be X. And if it's true, then the family contains Y, and Y is above X, so therefore the supremum must be Y. So with excluded middle, this is just completely trivial, and there's nothing to be gained. But constructively, it's a little bit subtle. So if you assume that X is not equal to Y, then it is the case that the supremum of delta is X, if and only if not P holds. But in general, you only have that P implies that the supremum is Y, but the supremum being Y only implies the double negation of P. So you have to introduce this double negation here, which is a little bit subtle. And then the two element poset, if this were delta U complete, then weak excluded middle holds. So constructively speaking, we don't expect the two element poset to be delta U complete. So it is not a trivial notion, constructively speaking. However, there's still a lot of examples, because every U-sup-lattice and U-DCPO and U-bounded complete poset and you name it is delta U complete, because this family is bounded and directed when X is below Y. So there's, even though the notion is constructively interesting, there are still plenty of examples. So in particular, the running examples, omega U and the power set are delta U complete, as well as the DCPOs in the Scott model. So they're all captured by this class of delta U complete posets. So that's what we're going to be basing the theorem on, this notion of a delta U complete poset. And so next up, I need to say when these guys are non-trivial. And again, this turns out to be a little bit subtle. There's a very straightforward notion where you just say a poset is non-trivial if I have 2 points, one below the other, and they're not equal. right? So there's something in the order, and it's just not entirely collapsible. But it's rather weak because this is a negated proposition. So if you want to do anything sort of useful constructively out of that, you're going to have a difficult time doing so. And for delta U complete posets, you can come up with a better notion. And so that's the following. So it's a notion of strictly below. So an element X is strictly below Y if, first of all, X is below Y. Okay. And for every Z above Y and for every proposition, if Z is this equal to this supremum, this delta supremum, then you can actually get P. So remember that in general, you only get the double negation of P. Now you strengthen this to actually get P, to get something positive out of this. And then we make the definition that a delta U complete poset is positive if you have points X and Y such that X is strictly below Y. So if you're familiar with this, it generalizes a notion of positivity due to Peter Johnstone for locales, but it generalizes it to delta U complete posets. But I'm gonna illustrate this notion right now with some examples to hopefully clarify this a little bit. So the slogan is that positivity is to non-triviality what inhabitedness is to non-emptiness, right? So non-emptiness is a negative way of saying that you have something and saying it's not the empty thing. And so positivity is a positive way of saying non-triviality. So here are two examples. So in the power set, the empty set is not equal to set A if and only if A is non-empty, but the empty set is strictly below A if and only if A is inhabited. So this example directly sort of, captures the slogan. But another thing, good thing to look at is the second example, where in the type of propositions, the empty type is not equal to P if and only if not P holds, but it's strictly below P if and only if P holds. So it's a stronger version, a positive phrasing of this. Okay, so these are going to be our notions of non-triviality. It's going to have positivity and non-triviality. And you can sort of hint already that the positivity is going to relate to this full resizing, and the non-triviality is going to be this weaker resizing of the not stable ones. So in the end, we're going to have two results linking these two up. And so we're almost ready to state the full result. We just need to say what we mean by a small poset. So that's what I'm going to do next. First, we're going to talk about locally small. So a delta U complete poset is locally small if the true value X below Y is small for every X and Y. So the true value being small, meaning that it is equivalent to some type in U, right? I'm thinking of the universe U as a small type. And so this is just like in category theory. So we say for every 2 points, this Hom set, right? The order is a small true value. And a lot of examples are locally small, all of the running examples so far, as well as the large TCPOs. But then we make the following definition where we say a delta U complete poset is small if it is locally small and its carrier is small, right? So in other words, the carrier itself is equivalent to something in U. And the point is that this can sort of never happen unless you have propositional resizing. So this brings us to the two main results. So the first one is saying that there is a small non-trivial delta U complete poset if and only if you can resize the not stable propositions in U, which is a little bit unsatisfactory because now you have to have this weak resizing here. You only have this delta U, the not stable propositions. So we can do better and have full resizing of omega U, but then we have to change non-trivial by positive. So the positive phrasing allows us to have a stronger equivalence here. And just to sort of reiterate this, so without resizing, there are no small non-trivial DCPOs. So if you would like your DCPOs that you're working with or your U-sup-lattices to be small, then you have no choice but to assume resizing. There's simply no other way about it. And of course, if you have the resizing, then you just resize omega to get you an example of a positive delta U complete poset. So that's the other direction. The other direction is, of course, a little bit easier to prove. And again, these are theorems of HoTT. So there are no metatheorems, no reference to models to do this. You need to prove it within the system. Okay, so let me say a little bit about the proof, at least the high level sort of strategy. So the idea is that you're going to be using retracts. So there's an important map for any delta U complete poset with these points X below Y. which called capital delta, which simply takes a proposition and then sends it to the supremum of delta, like lowercase delta xyp. And so this map is going to be very important, because now what you do is you phrase non-triviality in terms of this map having a section. So a locally small delta U complete poset with these points is non-trivial precisely when this composite has a section. So the composite is just forgetting that the thing is not non-stable and then mapping the proposition to its corresponding sup with respect to x and y. And so now you have a nice sort of categorical way, if you like, of thinking of non-triviality as this map having a section. And of course, there's a corresponding result for positivity, where now you have to say for every z above y, this map, and now we no longer need to restrict to the not non-stable ones, we can just take all of omega, this map has a section. Okay, so now we have these two sort of non-triviality properties in terms of sections, and that brings me to the next point, namely the size in sections. So there's a lemma which you can prove, which is that if S from A to B is a section and B is a small set, then A has to be small as well, which intuitively makes sense because if you can sort of embed all of A into a small set, then you would expect A to be small as well. It would be weird if you can embed something very, very large in something small. And so you can prove this lemma, and then almost immediately the theorems follow, because let me sort of say a few words about the second one. If you have a positive delta U complete poset, let's call it X. Now you have, because it's positive, you now have a section from omega U to X, but X is a set, and this map was a section, therefore by the lemma, omega U had to be small as well, which immediately gives you this omega U resizing. So through this theory of size and retracts, you can quickly and sort of nicely get these results. Right. Okay. So then I would like to mention just two like nice byproducts in a way of this technique. So another thing about retracts is that if you types with decidable equality are closed under retracts. So there's a very sort of easy lemma to prove. But the point is that this means that if you have a delta U complete poset, so remember this can be a U-sup-lattice or a DCPO or a bounded complete or whatever, you simply cannot expect them to have decidable equality. So we already knew that, at least from without a resizing standpoint, they're necessarily large, but constructively speaking, you cannot expect decidable equality. And the reason is, again, that let's do it for a positive one. So if you have a positive delta U complete poset with decidable equality, now you use the retract again. So omega is a retract of this poset, but if the poset has decidable equality, then so did omega. But if the type of propositions has decidable equality, now you can just decide every proposition. So this gives you exactly excluded middle. So in other words, you can never expect a delta U complete poset, if it's positive or non-trivial, to have decidable equality, because it would mean you have to accept either excluded middle or weak excluded middle already, which of course constructively you don't want to do. So the takeaway here is really that these objects are sort of very complex in a way from a constructive and a predicative viewpoint. Okay, so I'm almost out of time, so let me wrap up. So the take-home message is that non-trivial and positive U-sup-lattices, DCPOs, bounded complete posets, etc., all of these sort of weakly complete posets, they can only be small if these resizing axioms are assumed. So not ones for the non-trivial things, and positive, you can have the full omega resizing. And so without propositional resizing, some universe level management is necessary. Just like in category theory, you have to pay attention to the sizes. And in particular, the DCPOs in the Scott model of PCF are necessarily large. And then at the end, we saw this nice byproduct where non-trivial or positive, locally small U-sup-lattices, DCPOs, etc., can only have decidable equality if weak excluded middle is assumed. So they're sort of very, very interesting from a constructive viewpoint. So finally, I would like to say a few words about some other results in the FSCD paper. So we showed that various fixed point lemmas crucially rely on propositional resizing, as well as Zorn's lemma, which so we take a formulation for DCPOs, and this implies propositional resizing. but not exclude middle. And finally, we compare completeness with respect to families, which we saw here, where you have this, like in category theory, with respect to sort of the more traditional notion, where you ask for all subsets, and we sort of compare how they stack up in a setting without resizing. So with that, thank you for your attention, and I'm open for any questions.
Great, thanks. Let's silently applaud the speaker. And yeah, if anyone has a question they want to ask in front of everybody, we can take a couple of those and then we'll move to gather time.